All right. So, guys, so there is a thing called an ideal gas. An ideal gas. Okay. Now, there are different characteristics to an ideal gas. Now, when you think of a gas, what do you think of?
Gas in the car or something, like gasoline.
Like a solid liquid gas.
Gas. Carbon
Air. You think of air, carbon dioxide. Okay. What if you think about like the particles? What do you think about the particles?
They move very fast.
They move very fast. Ooh, I like that.
It's hot.
Particles move fast. Okay. They're small. Heard that. Particles are small. Let's see. What did you say, T? What?
It's hot.
Gets hot. They increase speed with temperature. I like that. They increase movement. Now, what's crazy is I got a jar. There's my jar. It's tightened, right? It's closed. If you have gas particles in here and you heat it up, they're going to start moving quicker. They're going to move very, very fast. However, what's crazy is these particles can hit each other. They bounce off of each other. Okay. Now, in an ideal gas, there's no loss of energy. There's no loss of energy, which is kind of crazy. Now, if you think about it, gotta draw this up real quick. There we go. Let's see. Justin, what question for you? Okay. When we're thinking about water, one, two, or three, ice. One. Okay. Seems pretty straightforward. Does everybody agree with that? If we're talking about water, everybody agree with one being ice? Huh. It is not one.
It's not. Wait, that's three.
Ice would actually be two. So when you have put water in the freezer, ice actually expands. Okay, and when ice expands, when you put ice in a cup of water, the ice actually floats to the top, right? It's less dense. Okay, so that's water. Okay, different particles. Okay, and then the gas is down here. That's the gas. Okay, now, an ideal gas does not have a volume. Does not have a volume. Let's see. I think we got all the other ones. Yeah, we nailed it. Okay. How do we feel on that? Does that kind of describe a gas? Russ, T, what are we doing? Am I speaking Spanish right now? Guys, come on. What are we doing? All right. So there's an equation that goes along with ideal gases. Okay. And it's pretty straightforward, okay? Pretty straightforward. And honestly, we're going to start with the big overall equation. We're going to start big and then break it down into smaller ones as we go through the weeks. Okay? The big equation is PV equals NRT. Okay. When we're thinking about gases, what do we think P might stand for?
Pressure.
Pressure.
Pollution.
Pressure is correct. Okay. There we go. P stands for pressure. And pressure is measured in a thing called atmospheres. Okay. V. What do we think V is? Volume. Volume. And that is measured in a thing called liters. Ooh. N is kind of tricky. N is just moles.
Why isn't it M?
Because M, a lot of people get that confused with like meters or miles or mass, momentum. So N is moles. R, I'm going to tell you R. R is always going to be 0.0821. 0.0821. So when you're solving this equation, solving this problem, what's R going to be?
0.8.
When you're solving this problem, what's R going to be? Every problem, 0.0821 is going to be R. Okay? And last but not least, T. What's T stand for?
Temperature.
Temperature. Temperature.
What does R stand for?
It's the R constant. I got Google. Let me Google it. That's a great question. What does R stand for in ideal gases? It stands for the universal gas constant. That's what they give me. Okay? And temperature. Temperature is actually measured in
Kelvin.
Kelvin. That's what we're focusing on. Okay, so there we go. That's the big equation. Pressure times volume is equal to moles RT. Okay, sound good? Okay, now, do you guys know what a piston is?
Yes. The thing in Minecraft is really
Really?
like hydraulics.
I'm intrigued. I've never played Minecraft, but I'm very much intrigued. Now, what a piston is in a car looks like that, and they go up and down very fast. Right?
It's what makes the wheels go around.
Now, so let's say I'm going to draw the particles like this. Okay. Now, when you increase the pressure, of my container, what happened to the particles?
It got tighter.
It got tighter, right? So the piston starts up here. As it's pushed down, the particles get closer and closer. So as the pressure increases, the volume would have to decrease. Just showing you some relationships. As the pressure increases, increase in pressure, the volume gets smaller. Tiandre, How you doing? We said this one earlier. If you increase the temperature, if the temperature increases, how does that affect the volume? It expands, right? So if temperature increases, volume increases. Crazy, crazy, crazy. So just some examples, okay? Sound good? All right, we're gonna go over one big problem on the board, and then we'll let you guys loose, okay? One big problem. There's a question. Now, when you guys get questions like this, I would recommend writing it all down. What do we know? Okay. So, for example, let's see, Russ, how you doing today? You good? Russ, do I have pressure anywhere? Do I have ATMs, atmospheres, anywhere in that problem? How many ATMs do I have? 3. Okay, I'm going to put a 3 right there. Let's see, Ethan, how are you doing today? Good. Volume, do I have volume over there anywhere? No? So that's what I'm solving for? There's no liters over there? There is? How many? 15. So that's 15. Timmy, do I have moles over there?
No.
No, I'm solving for moles. Okay, so I'm going to leave moles right there. Let's see. Maddie, do I know what R is? What's R? Every single time. Perfect. 0.0821. Oh, that's supposed to be 1. Mini 1. There we go. Okay. Let's see. Maya, how are you today? Do I have a temperature over there in kelvins?
Oh. Wait. Oh, yeah, it's okay.
I do?
75.
75. So guys, that's how you would set this problem up. Okay, you can multiply those two and multiply these two. Okay, so let's do that real quick. So I'm going to have 0.0821 times 75. So I got 6.1, we'll round, 6n. How do I solve for n? Divide both sides by 6.16. Okay, I got my answer to be 7.3. Does that make sense? Okay. Now,
It would take 7.3 CO2 moles.
say what?
Have a system of 15 liters, 75,000 Kelvin or 75 Kelvin.
For an ideal gas, yes. Yes. That's the perfect gas. Okay. So, boom, question. Yeah, absolutely. So guys, today's kind of an easy going day. Okay. We gotta walk around. There's problems around the room. All right, there's problems on the tables. What's awesome about it is I'm not collecting any of this because I just introduced it to you. Yeah, absolutely. Okay, I'm not collecting it. And even better, you guys can use whiteboards if you want to do your work since I'm not collecting it. Even better, everyone has an answer. Oh, right? That's pretty crazy. Every single one has an answer so you can check yourself. All right, guys, like I said, this is probably the most complex we're going to get in this chapter.
Really? I feel like it was easy. Last chapter meant.
Yeah, the last chapter, like, it ain't
The last chapter.
it got worse towards the end.
Got worse as we went. This is probably the most complex. Right?
I mean.
Read out reaction for more complex.
Well, this complex for this chapter. So, what I want you guys to do